Let's prove that odd of C over R only has two elements, the identity and complex conjugation. So in other words, we want to prove that odd of C over R is isomorphic to Z mod 2. There's only one group with two elements, that's Z mod 2, and so we want to show that odd of C over R only has two elements. In other words, we'll show that it's isomorphic to Z mod 2. Okay, so in order to prove this, we really need one fact. There's one key fact, and that is as follows. Let sigma be an automorphism of C over R. Then sigma of I has to be 0 of the polynomial x squared plus 1. And the punchline, sort of the result that we get out of this, the thing which we want more immediately, is that sigma I has to be either I or negative I. So I and negative I are the only roots of x squared plus 1. And thus sigma I, since it's a root of this polynomial, has to be equal to one of them. Sigma I has to either be I or negative I. So let's see why this is true. Let's see why this fact is true. Well, the fact is that I has to satisfy this polynomial, right? This polynomial wasn't just some random one. The reason why sigma I has to be a 0 of it is because I is itself a 0 of it. So let's see that. So we know that I is a root of this polynomial. We know that I squared plus 1 is equal to 0. And that tells us that, well, 0 is equal to sigma of 0, which is equal to sigma of I squared plus 1, because I squared plus 1 is just equal to 0. And then using the properties of sigma, we can rewrite sigma of I squared plus 1 as sigma of I squared plus 1. So sigma of I squared plus 1 is equal to 0. Sigma of I squared plus 1 is equal to 0. So sigma has to satisfy this polynomial, or sigma of I has to satisfy this polynomial, and thus sigma of I is either equal to I or negative I. So that's why this fact is true. Okay, so now let's use this fact to prove that odd of C over R only has two elements. So now we can prove the main claim. Proof of main claim. And the proof is as follows. So remember, we're trying to show that odd of C over R only has two elements, the identity and complex conjugation. That's what we're trying to show. And the way that we'll do this is to notice that any sigma inside of odd of C over R is entirely determined. It's totally determined by what it does to I. So sigma I tells us the whole picture. Sigma I tells us basically everything there is to know about the automorphism sigma. And the reason for that is any complex number can be written in the form a plus b I, for a and b real numbers. So any complex number can be written in the form a plus bi, with a and b real. So given that form, we see that sigma of a plus bi, by the properties of sigma, is equal to a plus b times sigma I. So sigma of a plus bi is a plus b times sigma I. And notice that the only things which are undetermined here is sigma I. Sigma I is kind of the only degree of freedom we have, because a has to get mapped to a and b has to get mapped to b. So a plus bi has to get mapped to a plus b times sigma I. Sigma I is kind of the only thing which matters. It's the thing which totally determines sigma. Okay, so given that we know that sigma of I is either I or negative I, we know what sigma of a plus bi has to be. So on one hand, if sigma of I is equal to I, then sigma of a plus bi is equal to a plus bi. So this happens if sigma of I is equal to I. And this function, of course, the function that we get out of this possibility, that's just the identity. And the other option is when sigma of I is equal to negative I. That's the other option. And in that case, sigma of a plus bi is equal to a plus b times negative I, which is a minus bi. So this happens if sigma of I is equal to negative I. And of course this function, this guy down here, is just complex conjugation. Complex conjugation. So we're done. Now let me briefly review the argument. So we want to show that sigma is either the identity or complex conjugation. And we've shown from the fact above that sigma of I is either equal to I or negative I. There are no other possibilities. So we know that sigma of A plus BI is either equal to A plus BI. That's what happens if sigma of I is equal to I. Or the other possibility is that sigma of A plus BI is equal to A minus BI. Those are the only two possibilities. Those are the only two things that sigma of A plus BI could possibly be. Sigma of A plus BI is either A plus BI, or sigma of A plus BI is equal to A minus BI. Those are the only two options, and while option number 1, that's just the identity, and option number 2, that's just complex conjugation. So we've proven the main claim. We've got what we desired.